Okay, let's dive right in. So picture this for a second. Your heart, it beats something like 100,000 times every single day.
Yeah, it's incredible. Adds up to, what, 3 billion beats in a lifetime. Just mind-boggling.
Totally. And what's amazing is that rhythm, it's not like your brain is constantly telling it, beat now, beat now.
No, exactly. It's all down to this amazing self-contained electrical system inside the heart muscle itself.
Right. And this system, it has what, two main jobs?
That's right. First, it has to generate those electrical impulses, with its own steady rhythm. And second, it needs to conduct them super fast, but also with very precise timing through the whole heart.
Okay, timing. That seems key. When it works right, the sequence is perfect, isn't it?
Absolutely. The atria need to contract just a fraction of a second before the ventricles. Gives them time to fill up with blood.
That little pause, crucial.
And then, maybe even more critical, almost all parts of the ventricles need to contract, well, pretty much simultaneously.
For that powerful squeeze, right?
Yeah.
To pump the blood effectively.
Exactly. That synchronized contraction is what generates the pressure. But, as the material points out, this system, as amazing as it is, it's also...
Well, it's vulnerable.
Yeah, things like heart disease, especially ischemia where blood flow gets restricted, they can really mess with this electrical setup.
Severely. And that can lead to all sorts of bizarre rhythms or the heart contracting in a really inefficient, uncoordinated way.
Which can really impact pumping, sometimes dangerously so.
Definitely.
Yeah.
So our goal today, really digging into this material you wanted to cover, is to go deep. Like really understand this specialized excitatory and conductive system.
Yeah.
You want the professional level detail.
Exactly. The components, the pathways, the timing, the cellular stuff. All of it.
Then that's what we'll do. Let's break it down, build that understanding.
Okay, so the big picture first. The main parts of this electrical engine.
Right. Think of it like a circuit. The starting point, the spark plug, if you like, is the sinus node, the SA node.
Got it. SA node starts it. Then the signal spreads out across the atria through some specific pathways called internodal pathways.
Okay, across the top chambers. Then what?
Then it hits a really important junction box, the atrio-ventricular node. The AV node. This is where that critical delay happens.
Ah, the pause we mentioned, to let the ventricles fill.
Precisely. After that pause, the signal gets funneled into the AV bundle, which then splits really quickly into left and right bundle branches.
And these branches are made of?
Specialized fibers called Purkinje fibres, super fast conductors. They spread the signal all through the ventricles.
Okay, so the basic flow. SA node fires A spreads through atria via pathways. Delay at AV node shoots down AV bundle and Purkinje fibers into the ventricles. That's the map.
That's the map. Now let's zoom in on the starting point, the SA node, the natural pacemaker.
Where exactly is it located?
It's in the upper part of the right atrium on the back side wall, just below and a bit to the side of where the superior vena cava enters.
And physically, is it large?
No, surprisingly small, actually. It's described as a little flattened strip, maybe 3 millimeters wide, 15 long, only about 1 millimeter thick.
Tiny. And the cells themselves are different too, right?
Very different. They're specialized cardiac muscle fibers, yes, but much smaller than the regular atrial muscle cells around them, like 3 to 5 micrometers across versus 10 to 15. And crucially, they have almost no contractile filaments.
So they're not built for squeezing, just for generating the electricity.
Exactly. Their whole purpose is that automatic electrical rhythmicity, self-excitation. That's their superpower.
And that's why it's normally the pacemaker, because it just naturally fires faster than anything else.
That's the core reason, yeah. Its intrinsic rate is the highest in the heart's conduction system, so it sets the pace for everything else. Ordinarily, anyway.
Okay, now the really deep part. How does it do that? The mechanism. This gets into membrane potentials, ions.
It does, and it's different from, say, your typical ventricular muscle cell. Those have a pretty stable, very negative resting potential between beats, maybe neg 85 or neg 90 millivolts.
But the SA node cells are less negative.
Right. Their resting potential isn't really stable. It fluctuates, but it hangs out around negative 55 to negative 60 millivolts. Significantly less negative.
So why is it less negative then? What's the key difference?
Well, the big thing is, these sinus node cells, their membranes are naturally a bit leaky.
Leaky to what?
To positive ions, specifically sodium and calcium. So even when the cell is supposed to be resting between beats, there's this slow, constant trickle of positive charge leaking in.
Ah, okay. And that's the key to it firing automatically. that inward leak.
That's the fundamental basis for it, yeah. That leakiness drives the self-excitation. Now, if we think about the ion channels involved...
Right, like the ones in regular heart muscle.
Hmm.
Sodium, calcium, potassium channels.
Yeah, but they function a bit differently here. Remember how ventricular muscle uses those fast sodium channels for that really rapid upstroke of the action potential?
Yeah, the big spike.
Well, in the SA node cells, because that resting potential is already less negative, around NMFE 55 millivolts, those fast sodium channels, they're mostly inactivated, blocked, essentially.
The voltage isn't low enough for them to be ready to open.
Exactly. So the action potential, the electrical firing in the SA node, isn't caused by a rush of sodium through fast channels.
So what causes it then?
It's primarily driven by the opening of L-type calcium channels, sometimes called slow calcium channels. They open more slowly than the fast sodium channels, but they let calcium ions flow in.
Calcium instead of sodium for the main upstroke. Interesting. And that makes the action potential different.
It does. It develops more slowly, and the whole process of returning to the negative state, repolarization, is also slower compared to the ventricular fibers. Now, to get the rhythm, we need to look at what happens between those
The
firings.
slow drift upwards on the diagrams, between beats.
Precisely that drift. After one action potential finishes and the membrane gets negative again, that slow inward leak of positive ions, sodium and calcium, just keeps happening.
Through those leaky channels. Anything specific?
Yeah, part of this leak is attributed to what are often called funny current channels, or if channels. They let some sodium in, contributing to that slow depolarization, but it's the overall inward leak of positive charge.
Okay, so positive charge is slowly building up inside again.
Right. It makes the membrane potential slowly drift upwards, becoming less and less negative.
Until it hits a trigger point.
Exactly. When that slow drift reaches a specific threshold voltage, usually around negative 40 millivolts, that's the trigger for those L-type calcium channels to snap open.
And that causes the main action potential, the firing.
Yes. The opening of those calcium channels lets in a bigger wave of positive calcium ions, causing the depolarization, the beat initiation. So fundamentally, the inherent leakiness causes the slow drift to threshold, which triggers the firing. That's self-excitation.
Okay, that makes sense. Leak, drift, mice, threshold, mass fire.
But why doesn't it just stay fired up? How does it reset? Good question. It needs to repolarize. Two main things happen. First, those L-type calcium channels that cause the firing, they don't stay open forever. They naturally inactivate or close after about 100 to 150 milliseconds.
So the main inward positive current stops.
Right. And at pretty much the same time, a different set of channels opens. Potassium channels. Potassium ions, K+, are highly concentrated inside the cell.
So when potassium channels open, potassium rushes out.
Exactly. Lots of positive potassium ions flow out of the cell. This outward movement of positive charge makes the inside of the cell negative again.
Inward calcium stops, outward potassium starts, drives the potential back down.
Precisely. That combination terminates the action potential. But there's one more subtle, really important detail for the rhythm.
Oh, what's that?
Those potassium channels, the ones that open to drive repolarization, they stay open for a little bit longer, maybe a few tenths of a second, even after the potential has returned to its negative state.
So potassium keeps flowing out even after it's negative.
For a short time, yes. And because positive charge is still leaving the cell, it actually makes the inside extra negative for a brief moment at the very end of the action potential. It dips down below the usual met at 55 or negative 60 millivolts.
That sounds like hyperpolarization. It overshoots.
That's exactly what it is. Hyperpolarization, maybe down to negative 60, negative 65 millivolts briefly.
Okay, so how does it get back up to start drifting again?
Because that hyperpolarization is temporary, over the next few tenths of a second, those potassium channels gradually close, so the outward flow of potassium decreases.
And meanwhile?
Meanwhile, that slow, persistent inward leak of sodium and calcium is still going on. As the outward potassium current fades, the inward leak starts to win again.
The inward leak starts pushing the potential back up from that hyperpolarized state.
Exactly. The membrane potential begins its slow upward drift again, heading back towards that negative 40 millivolt threshold once it hits it.
Boom. The L-type calcium channels open, and it fires again. The cycle repeats.
You've got it. Leak causes drift to threshold, calcium influx causes firing, calcium channels inactivate, and potassium influx causes repolarization. Lingering potassium efflux causes brief hyperpolarization. Potassium channels close, allowing inward lead to dominate again, causing the next drift to threshold. That's the engine.
Wow. That is intricate. Such a precise dance of ion channels and voltages.
Okay.
Okay, so the SA node fires. How does that signal get out to the rest of the heart?
Well, it spreads directly into the atrial muscle cells that are right next to the SA node, like ripples spreading out.
So just through the regular muscle of the
It
atria?
does travel through the general atrial muscle, yeah.
Oh, yeah.
But the conduction speed there is, well, relatively moderate, around 0.3 meters per second.
Not super fast.
No, but there are also specialized fast lanes, specific bands of atrial fibers that conduct the impulse much more quickly, about 1 meter per second.
Expressways for the signal. What are they called?
There's one key one called the anterior interatrial band, often called Bachmann's bundle, that sheets the signal directly over to the left atrium. Very important for making sure both atria contract together.
Makes sense. And the others?
Then there are 3 pathways, the anterior, middle, and posterior internodal pathways that curve through the walls of the right atrium and head straight for the AV node.
And these pathways are faster because?
They contain specialized conduction fibers, a bit like the Purkinje fibers we'll talk about in the ventricles. They're just built for faster signal transmission.
Okay, so fast tracks lead to the AV node. But then, as you said, things slow right down.
Dramatically. The AV node sits in the back wall of the right atrium, right behind the tricuspid valve. And its main job, its absolute critical function, is to delay that impulse before it gets to the ventricles.
And we know why. To give the atria time to empty, let the ventricles fill up properly before they squeeze.
Exactly. Without that delay, pumping would be really inefficient.
How long is this delay, roughly? We need the specifics for that pro-level understanding.
Okay, let's track it. From the SA node firing, it takes about 0.03 seconds for the impulse to travel through those internodal pathways and arrive at the AV node.
Okay, 0.03 seconds to get there.
Then the major slowdown happens within the AV node itself. That adds another delay of about 0.09 seconds on average.
Wow, almost a tenth of a second just crossing the node.
Yeah. And there's even a bit more delay, about 0.04 seconds, in the next part, the bit of the AV bundle that actually penetrates through the fibrous tissue separating atria and ventricles.
So total delay in the AV node in that penetrating bundle part is 0.09 plus 0.04. That's 0.13 seconds.
Correct. So if you add the 0.03 seconds it took to get to the node, the total time from the SA node firing until the signal actually gets into the main part of the AV bundle in the ventricular septum is about 0.16 seconds, a significant pause.
Definitely. What causes that slowdown physiologically? Why is conduction so slow there?
It seems to be mainly because the cells in the AV node and that initial part of the bundle have far fewer gap junctions connecting them compared to other cardiac cells.
Gap junctions. Those are the little tunnels that let the electrical current pass directly between cells, right?
Exactly. Fewer gap junctions means it's much harder for the ions carrying the signal to pass from one cell to the next. It creates a high resistance to conduction, slowing the signal way down.
Like trying to funnel traffic through a single lane after a multi-lane highway.
That's a pretty good analogy, yeah. But once the signal gets through that slow zone and into the main ventricular conduction system,
it speeds up again. Big time.
Massively. It enters the Purkinje system. These Purkinje fibers, which make up the rest of the AV bundle and the bundle branches, are totally different. They are very large cells, even bigger than regular ventricular muscle cells.
And they conduct incredibly fast.
Extremely fast. We're talking 1.5 to 4.0 meters per second. Compare that to the 0.3 meter sec in atrial muscle, or the super slow speeds in parts of the AV node.
That's maybe 6 times faster than normal ventricular muscle, and like 150 times faster than the slowest parts of the AV node. Huge difference.
It is, and that speed is absolutely vital. It allows the impulse, after its delay, to be distributed almost instantaneously throughout the entire inner surface of the ventricle.
Ensuring that near simultaneous contraction we talked about.
Precisely.
And why are they so fast? Lots of gap junctions.
Exactly the opposite reason for the AV node slowness. Purkinje fibers have a very high density and high permeability of gap junctions at their intercalated discs. Ions just flow easily from cell to cell with very little resistance.
Built for speed. Do they contract at all?
Very little, if at all. They have very few contractile myofibrils. Their job is purely electrical conduction.
Okay. Now that AV bundle, the connection between the atria and ventricles, it has another important feature, right, besides the delay?
Yes, a very important one. It's normally the only electrical pathway between the atria and the ventricle.
The only way through. Why is that?
Because everywhere else, there's a continuous sheet of fibrous connective tissue separating the atrial muscle from the ventricular muscle. This fibrous tissue acts as an electrical insulator.
So the signal can't just leak across from atrial muscle to ventricular muscle anywhere it wants. It has to go through the authorized gate, the AV bundle.
Exactly. This ensures proper timing And, critically, prevents the impulse from potentially traveling backward from the ventricles to the atria, which could cause chaotic rhythms. It enforces one-way traffic normally.
Though you mentioned sometimes there can be abnormal connections.
Yes, occasionally people have abnormal extramuscle pathways called accessory pathways that breach this fibrous barrier. These can bypass the AV node or allow reentry, leading to certain types of serious arrhythmias, but normally it's just the AV bundle.
Got it. Insulation is key. So the signal passes through the AV bundle into the ventricles. How does the Purkinje system spread it out from there?
Okay, so after penetrating the fibrous barrier, the AV bundle runs down the ventricular septum, the wall between the ventricles for a short distance, maybe 5 to 15 millimeters. Then it splits.
Into the left and right bundle branches.
Correct, one for each ventricle. These bundle branches travel down towards the bottom tip, the apex of the heart, running just underneath the inner lining, the endocardium.
And then they branch out further.
Yeah, they divide again and again, spreading sideways around the walls of the ventricles and looping back up towards the base of the heart.
Covering the whole inner surface.
Pretty much. And the terminal Purkinje fibers actually penetrate about a third of the way into the thickness of the ventricular muscle wall before they connect with the regular ventricular muscle cells.
Delivering the signal deep inside, not just on the surface. How long does this distribution take through the Purkinje system itself?
Incredibly fast. From the moment the impulse enters the bundle branches in the septum until it reaches the very ends of the Purkinje fibers where they connect to muscle, it only takes about 0.03 seconds.
Wow. So in just 0.03 of a second, the signal is delivered almost simultaneously to the entire inner layer of both ventricles.
That's the power of that rapid Purkinje conduction.
Yeah.
Now, once the signal leaves the Purkinje fibers and enters the ordinary ventricular muscle,
It slows down again.
yes, back to that more moderate speed of about 0.3 to 0.5 meters per second. The muscle cells are designed for contraction, not super fast conduction.
And the muscle fibers are arranged in a spiral.
Right. That complex spiral arrangement means the impulse doesn't just travel straight outwards, but kind of angles towards the outer surface, the epicardium. Getting from the endocardium, where the Purkinje fibers end, through the muscle thickness to the epicardium takes another bit of time.
How long for that last step through the muscle?
About another 0.03 seconds.
Okay, so let's put that together. 0.03 seconds for the Purkinje system to distribute the signal to the inner layer, and then another 0.03 seconds for it to travel through the muscle thickness to the outer layer.
That's right. So the total time from when the impulse first enters the bundle branches until the very last bit of ventricular muscle is excited is remarkably short, only about 0.06 seconds in a healthy heart.
0.06 seconds to activate the entire ventricular mass after the AV delay.
Yeah.
That's impressive coordination.
It really is.
Okay, let's quickly recap the whole timing sequence then, just to lock it in. This seems absolutely fundamental.
Good idea. Start clock at SA node firing, 0.00 seconds.
Signal travels through atria, reaches AV node area around 0.03 seconds.
Then the big delay kicks in AV node and penetrating bundle take over a tenth of a second. So the signal doesn't actually enter the main ventricular conduction system until about 0.16 seconds.
Right, 0.16 seconds. Then super fast spread via Purkinje fibers to all the endocardial surfaces. That takes it to about 0.19 seconds total.
Yep. And finally, conduction through the ventricular muscle mass itself from inside to outside takes another 0.03 seconds or so, meaning the entire ventricle is activated by around, say, 0.22 to 0.25 seconds after the initial SA node beat.
Roughly a quarter of a second for the whole journey, SA node to final ventricular muscle fiber.
Got it. Understanding that sequence is crucial.
Absolutely. It's the basis for understanding ECGs and diagnosing rhythm problems.
Which brings us to control and what happens when things go wrong. We said the SA node is usually the pacemaker because it's fastest. Right. Its intrinsic rate, 70-80 beats per minute typically, is faster than the AV node's backup rate of 40-60 and much faster than the Purkinje fibers rate of maybe 15-40 BPM.
So the SA node signal gets everywhere else first and resets them before they can fire on their own. It overdrives them.
Exactly. It suppresses their latent pacemaker activity. But sometimes other parts do take over.
Ectopic pacemakers.
Yes. An ectopic pacemaker is just any site other than the SA node that starts firing rhythmically faster than the SA node or takes over if the SA signal gets blocked. Could be the AV node, Purkinje fibers, rarely even atrial or ventricular muscle itself if it becomes irritable.
And if that happens, the contraction sequence gets messed up, right? Because the signal isn't starting in the right place or following the normal path.
Precisely. It often leads to less efficient pumping because the timing and coordination are off.
A common reason for an ectopic pacemaker kicking in is AV block, you mentioned.
Yes, very common. AV block is when the impulse from the atria fails to get through the AV node or AV bundle to the ventricles.
So the atria keep beating normally, driven by the SA node.
But the ventricles don't get the message. So what usually happens is a spot lower down, often in the Purkinje system within the AV bundle or bundle branches, which has its own slow inherent rhythmicity, escapes the suppression and starts pacing the ventricles.
But at its own slow rate, that 15-40 beats per minute.
Right, which might keep the person alive, but it's often not enough for normal activity. And there's a particularly dangerous scenario related to this.
Stokes-Adams syndrome.
Yes, this can happen if the AV block occurs suddenly and completely.
What's the issue? Doesn't the escape rhythm just start?
Not always immediately. Because the Purkinje system was being constantly overdriven by the faster sinus rhythm before the block, it can take some time for it to wake up and start its own intrinsic rhythm. There can be a delay.
How long a delay?
It can be anywhere from 5 seconds to maybe 20 seconds, sometimes even longer.
And during that delay, no ventricular contraction.
No ventricular pumping at all, which means no blood flow to the brain.
And after just a few seconds without blood flow, you'd pass out.
Yeah, fainting typically occurs after just 4 or 5 seconds. If that delay before the escape rhythm starts is too long, it can cause severe brain injury or even death. It really highlights how critical that continuous conduction through the AV bundle is.
Wow. That backup system is vital, but the potential delay is terrifying.
Yeah,
It really drives home the importance of the primary pathway.
it does. Now let's circle back to why that fast Purkinje conduction is so important for the mechanical job of the heart.
Synchronous contraction again.
Yes, because the Purkinje system delivers the signal so quickly and widely, almost all parts of both ventricles get the contract now message within that tiny 0.03 to 0.06 second window after the signal enters the bundle branches.
So they all start squeezing at virtually the same instant.
Exactly. And they continue contracting together throughout the ejection phase.
And that coordination is essential for building up pressure efficiently.
Absolutely. Imagine if one part of the ventricle squeezed much earlier than another part. The force wouldn't be directed properly. Some muscle might be contracting while other parts are still relaxing or just starting. It wastes energy and reduces the pumping force.
How much impact does poor synchrony have?
The source suggests that if conduction through the ventricles is significantly slowed, leading to asynchronous contraction, the overall pumping effectiveness can decrease by as much as 20 or even 30%.
A huge drop in efficiency just from bad timing.
It really is. And understanding this is the basis for things like cardiac resynchronization therapy, or CRT.
The special pacemakers.
Right. In patients with heart failure, and often enlarged hearts where electrical conduction is slow and uncoordinated, CRT devices use multiple leads to pace different parts of the heart, maybe both ventricles, or different spots on the left ventricle to try and restore that synchrony and improve pumping.
A direct application of understanding this intricate electrical timing. Okay, last piece of the puzzle. The nervous system's control over all this.
Right, the autonomic nervous system. The heart gets input from both sides. Parasympathetic nerves, mostly via the vagus nerve, and sympathetic nerves.
Where do they connect?
The vagal fibers primarily go to the SA node and the AV node. There's less innervation of the atrial muscle and very little directly to the ventricular muscle.
Okay, vagus, mostly nodes. What about sympathetic?
Sympathetic nerves go everywhere. SA node, AV node, atrial muscle, and importantly, a very strong supply to the ventricular muscle itself.
So vagus nerve mainly controls heart rate and the AV node delay, while sympathetics influence rate, conduction speed everywhere, and the force of contraction, especially in the ventricles.
That's a great summary. Let's look at the parasympathetic, the vagal effect first. When the vagus nerve is stimulated, it releases the neurotransmitter acetylcholine.
Acetylcholine, and its effects are?
Two main things. It slows down the firing rate of the SA node, and it decreases the excitability of the fibers in the AV junction, slowing down conduction from atria to ventricles.
So vagal stimulation is the brake, slows heart rate, increases AV delay.
Exactly. Mild stimulation might just slow the rate a bit. Moderate stimulation could cut the heart rate in half. Really strong vagal stimulation can actually stop the SA node completely for a time, or totally block conduction through the AV node.
Leading to that potential ventricular escape situation again.
Potentially, yes. If AV conduction is blocked by strong vagal tone, that slow Purkinje rhythm might take over the ventricles. Now, how does acetylcholine do this? The mechanism.
The deep dive detail.
Acetylcholine significantly increases the permeability of the cardiac cell membranes, especially in the nodes, to potassium ions, K+.
More potassium permeability, so potassium flows out of the cell more easily.
Correct. And since potassium ions are positive, losing more positive charge makes the inside of the cell more negative. It causes hyperpolarization.
So in the SA node, if acetylcholine makes the resting potential even more negative than usual, say -65 or -5 milliV instead of -55,
then it takes much longer for that slow inward leak of sodium and calcium to drift the potential back up to the -40 milliV firing threshold.
Wow.
Longer drift time means slower rate.
And if the stimulation is really strong,
The hyperpolarization might be so great that the inward leak just can't overcome the outward potassium current enough to ever reach threshold, the SA node stops firing.
and at the AV node, same hyperpolarization effect.
Yes. Hyperpolarization makes the AV nodal fibers less excitable. It takes a stronger signal from the atrial fibers to trigger them. This reduces the safety factor for transmission. Moderate vagal tone just increases the delay. Strong tone can block transmission completely.
So vagus nerve, acetylcholine, increased K+ permeability, hyperpolarization, slower SA rate, and slower blocked AV conduction.
Got it. Perfect. Now, the sympathetic nervous system, the accelerating.
Releases norepinephrine.
Right. Norepinephrine acts on beta-1 adrenergic receptors in the heart, and its main effect on ion channels is thought to be increasing the permeability to both sodium Na+ and calcium Ca2+.
So more inward positive current, opposite of the vagal effect on potassium.
Exactly, and the overall effects are pretty much the opposite too. Sympathetic stimulation, 1, increases the SA node firing rate. 2, increases the speed and excitability of conduction in all parts of the heart AV node, Purkinje system. 3, greatly increases the force of contraction of both atrial and ventricular muscle.
So faster rate, faster conduction, stronger squeeze, everything ramps up.
That's it. Maximum sympathetic drive can nearly triple the heart rate and double the strength of contraction.
How does the increased Na plus Ca2 plus permeability achieve this in the SA node?
The increased inward leak makes the starting resting potential slightly less negative, and more importantly, it increases the slope of that upward drift towards threshold. It reaches threshold faster, so it fires more frequently, higher heart rate.
And faster conduction in the AV node and Purkinje fibers.
Making it easier for sodium and calcium to flow in means the action potential propagates from cell to cell more quickly and easily. Less delay, faster speed.
And the stronger contraction, that's the calcium part.
Primarily, yes. Increased calcium influx during the action potential in the muscle cells directly leads to a stronger activation of the contractile machinery, the myofibrils. More calcium, stronger pump.
It's amazing how these two branches of the nervous system provide this constant push-pull, fine-tuning the heart's activity based on everything else the body's doing.
It really is an elegant control system, balancing braking and acceleration perfectly most of the time.
So we've covered the entire journey. From the SA node's incredible self-excitation mechanism, the atrial pathways, that vital AV node delay, the super-fast Purkinje network ensuring synchronous contraction, what happens with ectopic beats and AV block, like that dangerous Stokes-Adams pause, and finally how these sympathetic and parasympathetic nerves use specific ion channels to speed things up or slow them down. It's quite a system.
It truly is. The level of detail, the precision in timing and cellular function is just remarkable. Required for life, beat after beat.
Yeah. And considering all those details we just went through, the specific voltages, the ion channels like L-type calcium and that funny current, the millisecond timings, the gap junctions, the fibrous insulation, the neurotransmitter effects, you just have to marvel, don't you? How can this biological machine maintain such reliable, coordinated rhythm for potentially billions of beats over decades? And I guess, what is its vulnerability when things do go wrong? Tell us about just how fine that balance really is for life itself.
It's a profound question. It shows an incredible biological resilience, but also a fragility that underscores why understanding these mechanisms so deeply is absolutely critical when disease strikes that delicate balance. It's the foundation for effective treatment.